I'm dealing with a dataset containing 100 different observations. Each observation has 5 measurable characteristics, or features, and 3 outcomes I want to predict, called target variables. Think of it like predicting house prices, 3 different price ranges perhaps. And each house is described by 5 features: size, location, age, number of rooms, etc. I'm using MultiTaskLassoCV, a specific type of model from Sklearn, designed to predict multiple target variables simultaneously using a technique called lasso regression, which encourages sparsity by penalizing large coefficient values. That's a fancy way of saying it will find the simplest, yet accurate model to predict those 3 targets. I'm going to train this MultiTaskLassoCV model. I'll explain how this model works, its inner workings, and its final output. To ensure the model's accuracy isn't just luck on a single training split, I'm using 5-fold cross-validation. CV equals 5. This means I'll split my data into 5 equal parts. 4 parts will be used to train the model, and the remaining part is used to test it. This process repeats 5 times, with a different part used for testing each time. The model then picks the best settings using the average performance across these 5 tests. It's like testing a recipe 5 different times with slightly different ingredient amounts each time and choosing the one that produces the best result overall. After training, the model produces a coefficient matrix that's 5 rows by 3 columns. Each row represents one of my 5 features, and each column represents one of my 3 target variables. The numbers in the matrix are the coefficients, which indicate how much each feature influences the prediction of each target variable. The model also keeps track of the mean squared error, MSE, a measure of prediction accuracy, for different hyperparameter values called alpha during the cross-validation process. A lower MSE indicates better performance. This information helps me choose the best setting for alpha. This statement is incorrect. MultiTaskLassoCV doesn't fit 5 separate models. It fits a single model to predict all 3 target variables simultaneously. That's the power of multitask learning. This statement is also false. The MultiTaskLassoCV model selects a single best alpha value across all the target variables during cross-validation, not a separate one for each target. I'm working with a dataset containing 100 different observations. Each observation has 5 different characteristics, or features, and we're trying to predict 3 different outcomes, or target variables, for each observation. This is a multitask regression problem because we're predicting multiple outputs simultaneously. I will split my data into 5 equal-sized parts, or folds. I'll train my model on 4 of these folds and then test it on the remaining fold. I'll repeat this process 5 times, each time using a different fold as the testing set. This cross-validation technique gives me a more reliable estimate of my model's performance. I'm doing it this way because it helps avoid overfitting. I'll use Sklearn's MultiTaskLassoCV for this job. This model is perfect for the multitask learning setup and handles multiple targets with lasso regularization. Lasso regularization shrinks coefficients toward 0, helping with feature selection and preventing overfitting. The CV in MultiTaskLassoCV stands for cross-validation, which ensures a robust model. This attribute will store the calculated coefficients for my model. I'll have a 5x3 array because there are 5 features and 3 targets. Each element shows how much each feature impacts each target variable. It's going to be a really useful thing for understanding feature importance and predicting new values. The _alphas _ attribute will hold the single best regularization strength that MultiTaskLassoCV found across all the target variables during cross-validation. This is the single optimal alpha value after comparing the performance of all different alpha values tested. This attribute will store the mean squared error calculated during cross-validation. I'll have an error value for each alpha value and each target. This lets me see how my model performs with different levels of regularization. I'm fitting a single MultiTaskLassoCV model. It's not fitting separate models for each of the 3 target variables. Instead, it cleverly learns from all targets simultaneously. This is the core idea behind multitask learning. Share information across related tasks. I have a dataset with 100 data points. Each data point has 5 features, like weight, height, etc. And 3 things I want to predict, the targets. Think of it like trying to predict a person's weight, height and age given 5 other measurements. After training, I'll get 5 coefficients for each of the 3 targets. This gives a 5 by 3 array. Each of the 5 features will have its own set of 3 coefficients associated with the target variables. During the 5-fold cross-validation, I'll test various values of alpha, regularization strength, and compute the MSE, mean squared error. I'll do this for all 3 targets jointly for each alpha. This gives me a complete picture of how well my model performs with different amounts of regularization. After evaluating the MSE across all folds and all alpha values and all targets, I choose the single alpha value that provides the overall best performance. I don't pick a separate alpha for each target. I use one alpha value for all 3 prediction tasks. It's the best compromise across all of them. I'm using 5-fold cross-validation to prevent overfitting. I divide my data into 5 parts. Each time, I train on 4 parts and test on the remaining part. I repeat this 5 times, each time using a different part as the test set. This gives a more robust estimate of my model's performance on unseen data. I use a single MultiTaskLassoCV model. This model jointly learns the relationships between the features and all 3 target variables. The key is that it learns from all targets simultaneously to improve predictions for all of them. I'm working with a dataset containing 100 samples. Each sample has 5 features, and we're trying to predict 3 different target variables simultaneously. Think of it like trying to predict a person's height, weight, and age all at once using 5 different characteristics about them. To make sure my model generalizes well to new data, I'm using 5-fold cross-validation. This is like splitting the data into 5 parts. I train the model on 4 parts and test it on the remaining part. I repeat this process 5 times, each time using a different part as the test set. This gives me a more robust measure of how well the model performs, than just using a single train test split. I'm using scikit-learn's _multitaskLassoCV, which is a fantastic model that fits multiple regression problems, here, the 3 targets, at once. It leverages shared information across the targets to make more accurate predictions. Lasso, L1 regularization, is helping me keep my model simple by shrinking the less important coefficients closer to 0. The CV part means it does cross-validation to find the best hyperparameters. The model learns 5 coefficients, 1 for each of the 5 features, for each of my 3 target variables. Therefore, I get a 5 by 3 array of coefficients. Each row represents a feature, and each column represents a target variable. The model tries several different values of alpha, the regularization parameter, during the cross-validation. For each alpha, it calculates the mean squared error, MSE. The average squared difference between the predicted and actual values. The MSE_path_back_ attribute stores these MSEs so that I can choose the best alpha. The MultiTaskLassoCV model is designed specifically for solving multiple related regression problems simultaneously. It's not just fitting 3 separate models, it's leveraging the relationships between the targets to improve efficiency and prediction accuracy. After trying different alpha values during cross-validation, the model selects the single best alpha that minimizes the MSE across all folds and targets. This is the alpha value that results in the best overall model performance. I'm using MultiTaskLassoCV, which means I fit one model to predict all 3 target variables at once. I don't fit separate models for each target, instead, I leverage information across all of them to improve predictions. Think of it like learning to play multiple instruments at the same time. You're developing skills that benefit all instruments. Pretty cool, huh? I have 100 different observations or samples, each described by 5 features. My goal is to predict 3 different things, 3 target variables, for each sample. The model produces a 5 by 3 matrix. Each row represents a feature and each column represents a target variable. Each element in the matrix represents how much that particular feature contributes to predicting that specific target variable. For example, the element in the first row and third column tells me how much the first feature helps in predicting the third target variable. After trying multiple values, ALPHAS, I select a single best value for regularization strength, which helps to improve the overall model performance across all the target variables. I don't choose a separate value for each target because I'm treating them as related. To find the best ALPHA, I tested several values. For each, I calculated the mean squared error, MSE, a measure of prediction error, averaged across all three target variables. The path shows how MSE changes as ALPHA changes. This helps to choose a value that balances model complexity and prediction accuracy. I use five-fold cross-validation to help ensure my model generalizes well to unseen data. The data is split into 5 chunks. I train the model on 4 chunks and test it on the remaining chunk. I repeat this process 5 times, each time using a different chunk as the test set. I then average the performance across these folds to evaluate the model. I see a dataset with 100 samples. Each sample has 5 features, and we're trying to predict 3 different target variables simultaneously. That's what makes this a multitask learning problem. This is where the model stores its results. It's a 5x3 array because we have 5 features and 3 target variables. Each element represents how much each feature influences each target variable. Think of it as a coefficient matrix, showing the weight of each feature in determining each target. The model will calculate the mean squared error, MSE, for different values it tries during its search for the best fit. This helps to decide which setting works the best. MSE measures how far the model's predictions are from the actual values. This variable holds the value that controls the strength of the regularization for the model. The model tries out various values of ALPHA to find the best one that avoids overfitting while maintaining good prediction accuracy. It's like finding the right balance between making predictions and keeping the model simple. To ensure that the model generalizes well to unseen data, we use five-fold cross-validation. I'll split the data into 5 parts. Each time, 4 parts will be used for training and 1 for testing. The model's performance is evaluated by averaging over all 5 folds. This gives me a more robust measure of its performance. This is the core of the problem. We are using Scikit-learn's MultiTaskLassoCV algorithm. Multitask means it tackles multiple target variables at once. Lasso indicates that it uses L1 regularization. It shrinks less important feature weights toward 0. CV stands for cross-validation, which helps avoid overfitting. I'm working with a dataset containing 100 observations. Each observation has 5 features, think of them as characteristics or inputs. And we're trying to predict 3 different target variables. These are what we want to predict, like house prices, temperature, etc. To evaluate the model's performance reliably, I'll use five-fold cross-validation. I'll split my data into 5 equal parts. 4 parts will train the model, and the remaining part will test its predictions. I'll repeat this process 5 times, using each part as the test set once. This helps avoid overfitting and provides a better estimate of how well the model generalizes to new data. The model will output a 5x3 matrix of coefficients. Each row corresponds to one of the 5 features, and each column corresponds to one of the 3 target variables. The values within the matrix represent the weights assigned to each feature for predicting each target variable. These coefficients essentially show the importance of each feature in predicting each target. The model finds the single best value for alpha across all 3 targets. Alpha is a regularization parameter controlling the strength of the penalty applied to the coefficients. It helps prevent overfitting. The best alpha value minimizes errors across all my prediction tasks. During cross-validation, I'll track the mean squared error, MSE, the average squared difference between predicted and actual target values, for each alpha value during cross-validation. This path of MSE values helps determine the optimal alpha. I'm using Scikit-learn's MultiTaskLassoCV, which is specifically designed to tackle multiple regression tasks together. Lasso is a type of regression that adds a penalty to the model to shrink the coefficients toward zero, essentially encouraging feature selection, making the model simpler and less prone to overfitting. I'm using a multitask lasso regression model. This means I'm building one model that simultaneously predicts all three target variables. This is more efficient than training three separate models and also helps the model learn relationships between the targets.